Morning. Thank you for coming to my talk. My name is Weizhong Wang. I'm with Geothermal Houston. The main authors of the work are Hongfeng, Anthony Key, Anita Knudsen, with Husky Energy, now Cenovus Energy, and Amber Air with BP Canada. My talk, first I will review why Husky acquired 3D DAS data at their Sunrise SAGD project, and their objectives of performing this 3D FWI study. I will explain how DAS FWI works and show a 2D synthetic model test we did to prove the concept. I will also show a single DAS experiment Husky did with different sources. I will show the final 3D DAS experiment result and the lessons we learned at the end. Sunrise is a bitumen deposit located near Fort McMurray, Alberta, Canada. This onshore oil sands project is being jointly developed by Husky Energy and BP. Husky Energy operates the field. Bitumen from the Sunrise oil sands is produced by employing an enhanced oil recovery technology known as steam-assisted gravity drainage, SAGD. SAGD is applied by drilling a pair of the horizontal wells into the reservoir with a spacing of 5 meters. The upper well is used as the injector well, while the lower well is used as the producer well. Steam is continuously injected into the upper well to heat the reservoir bitumen and reduce its viscosity. This causes the heated oil to flow into the producer well, lower horizontal well, where it is pumped out. For the surface seismic data were acquired over the years in the field to monitor the steam chamber growth in order to reduce the risk of the next stage of development. Fiber optic sensor cables were deployed to provide a continuous well temperature profile for steam management and production optimization. To reduce the 4D surface seismic acquisition cost, it's obvious if we can acquire 4D DAS data in steam chamber monitoring. On a steam-assisted gravity drainage project, steam injected into the reservoir to produce bitumen. The replacement of bitumen with the gas phase produces a significant velocity variation. The output of FWI is a velocity depth model, which can be directly used for steam chamber interpretation. FWI deals with raw seismic shot records instead of a migration stack. The objective of this study is to investigate whether we can directly use DAS FWI result in steam chamber monitoring that will allow us to reduce the 4D analysis turnaround time. The FWI workflow is relatively straightforward, where we input the raw field data and match with the simulated data. If there's a mismatch, the misphase is backward projected to the Earth to update the velocity. FWI algorithm performs this update in an iterative way till it converges to a true velocity Earth model. This slide illustrates the FWI loop. The beauty of FWI is it directly produces an impedance like an image instead of a reflection amplitudes, so we can easily identify steam chambers. Its model has high resolution comparing with a conventional time delay analysis. It doesn't require many traditional processing steps, such as surface consistent decon and migration. But like other inversion methods, it suffers from an air post problem due to the limited data. It can cycle skip if the low frequency is missing in the acquisition. It can convert to a local minimum. To avoid this problem, Geothermal has a patented technology that can use the travel times to constrain the inversion. Husky first tested the Geothermal FWI process with a 2D synthetic model that has prop rock and steam chamber velocities. Fiber optic sensors were placed below the steam chamber anomalies. Finite difference forward modeling was performed to generate the synthetic wave field. Without giving the knowledge about the true model, 2D FWI tests successfully recovered the steam chamber anomalies. Here you see the true model versus the FWI result. Before carrying out the 3D data acquisition, Husky also tested the data responses with different source configurations. A single evaporator track versus a dual track source you see here in the image. The key component of a DAS system is the interrogator unit, which first sends pulses of a laser line into the fiber optic cable and then measures the phase of the backscatter line from the imperfections in the fiber. As these imperfections are jostled by seismic energy that hits the fiber, the backscatter line changes in intensity and phase. These phase changes are detected in the interrogator and are used to measure the relative strain in fiber optic cable. There are three major sources of optical noise typically observed on the DAS data: vertical noise, common mode noise or horizontal noise, drifting low frequency strain. We remove the noise and convert the DAS strain data to particle motion seismic before FWI. This slide shows what we have observed in the fiber size source test. The shot from a two-track source has better signal-to-noise ratio with stronger energy amplitudes, but it does damage high frequencies a little bit. For FWI, our focus is at low end of the frequency band. Clearly, a two-track source has its advantage. We are now going to show the result of the 3D DAS experiment. This slide shows the acquisition geometry. Fiber sensors were installed along each horizontal well. The fiber gauge length is 15 meters, and the fiber channel interval is 1 meter. There are 6 fiber cables with 100-meter spacing. The cable is marked with the number 1 to 6 from left to right. Each yellow dot represents a surface shot. The shot interval is 20 meters, and the shot line spacing is 40 meters. A surface 3D were acquired at the same time with the same shots. Here we show the quality of DAS data. The left panel is a superior quality shot selected from cable 6. The shot location is closer to the cable, and the cable has a good coupling. When the cable channel is almost directly below the shot, we observe the optical worst response. When running FWI, we typically remove these traces. The right panel of this slide shows a shot from cable 4 that has a bad coupling. The shot is also further away from the cable. Now we compare the 3D DAS FWI result with the 4D surface seismic FWI. To know more about what we did for 4D surface seismic data, you are welcome to attend Dr. Hong Feng's talk at the coming EAGE meeting. This slide shows a profile of the FWI velocity model difference of the surface monitoring survey across the yellow line on the map. On the map, the yellow line represents the surface monitoring survey, and the red line represents the surface seismic survey. The red line represents the surface monitoring survey, and the yellow line represents the surface seismic survey. The surface monitoring survey is the surface monitoring survey across the yellow line on the map. Select a line at the same location as the surface seismic data. We are showing you here the 3D data FWI result. Comparing with the previous slide, the 3D data FWI is quite similar like the surface 4D FWI, except at the area around the cable 4. Due to a coupling issue of the cable 4, the 3D data FWI result shows less thickness there. Other than that, the 3D data FWI is quite encouraging. A temperature log is also plotted on the left side of the velocity anomaly. The FWI result matches the temperature log nicely. We plot these two images on top of each other to allow you visually to compare the differences here. Here we have selected another profile at a different location. This is the 4D surface seismic FWI result. This slide is the 3D data FWI result at the same location. Plot them on top of each other. The 3D data FWI is quite same as the 4D surface seismic FWI near the cables. But between the cables, I have to say depth resolution is low. We extracted the body of the velocity anomaly and calculated a thickness map. Comparing with 4D surface seismic FWI, the results match well except around cable 4. Comparing with traditional time delay analysis using PSTM image, we're glad to see 3D data FWI actually shows a higher resolution. Now I'm going to play a movie to show you the model comparison slice by slice. The one on your left is 3D data FWI result, and the one on your right is 4D surface seismic FWI result. Both volumes were converted from depth to two-way times. This slide is a movie to show you the 3D data FWI model in 3D, so we can have a better view of inverted anomaly relatively to the injector and the producer wells. The view from different angles. To conclude my talk, we have demonstrated the preliminary 3D data FWI result shows a good agreement with well temperature logs, traditional PSTM time delay analysis, and 4D surface seismic FWI. Future studies can test the sensitivities of higher frequencies and finer cell size. If both surface seismic and 3D data are available, perform FWI with both datasets together may help to improve the depth resolution between the cables and the surface resolution near the wells. Thank you for attending my talk.